Just 40 years ago, a revolutionary concept, plate tectonics, changed the way we think about Earth. It helped explain Earth's most violent shudders, explosive forces, and even what gave rise to her tallest mountains. By understanding how and why the ground constantly shifts under our feet, geoscientists can show us what lies ahead.
The stresses build up, and then bang, we have an episode.
Look up. Look around. Look deep below. On this episode, we explore the shifting layers beneath our feet and how they alter the faces of Earth. Why is Earth so restless? What causes the ground to shake, volcanoes to erupt, and great mountain ranges to rise to incredible heights? The face of Earth is continually shifting, influenced by a process called plate tectonics. Earth's surface, the lithosphere, is a mosaic of many plates girdling the planet like seams on a baseball. These plates drift on top of Earth's hot and slowly churning mantle, over time colliding, breaking apart, and grinding against each other. To understand tectonics, scientists look back only 200 million years, because earlier geologic evidence has been either recycled or hidden by Earth's processes. "200 million years ago, all of the continental plates we know today had collided and formed a supercontinent scientists call Pangaea. The ancient Paleo-Pacific Ocean to the west and the Tethys Sea to the east surrounded it. Soon after its formation, Pangaea began to break apart, much like what is happening in Ethiopia today. A rift opened that separated North America, Africa, and Europe, giving birth to the Atlantic Ocean. That same rift, now called the Mid-Atlantic Ridge, is still in motion.
Analyzing core samples and sonar readings from around the Mid-Atlantic Ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
At these ridges on the bottom of the ocean, powerful convection currents in the mantle separate Earth's plates, allowing lava to spill out onto the seabed.
For years, oceanographers surveying the Atlantic Ocean had taken sonar readings that indicated there was something down there, something big. In 1953, they found out what it was, a 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge. To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
The ocean floor was progressively older the greater the distance from the crack. This was difficult to explain until scientists came up with a solution. It's a solution these students are about to demonstrate. This sheet of paper represents the seafloor beneath the Atlantic Ocean. The space between the table represents the crack in the ocean floor, the mid-ocean ridge. The numbers represent the age of the ocean floor at various distances from the mid-ocean ridge. The lower numbers represent older material. As the paper is spread apart, more paper emerges from the crack. As you continue, you can see how the lower numbers are spread farther and farther apart. This is the way scientists explained how it was that material farther away from the crack could be older than material found near the crack itself. This process is called seafloor spreading.
Remember how all these numbers were all even with all of these?
The Earth's surface is broken up into 7 major chunks called plates. They're so enormous that they can carry an entire continent and extend far under the sea. Strip away the Atlantic Ocean and you can see a long boundary between 2 of these plates that runs along the ocean floor until it rises above the waves, cuts through Iceland, to eventually join up with the rock face at Thingvellir.
This is Thingvellir. It's an important place in human history because in AD 930, a group of Icelandic chieftains gathered here to sort out their disputes. This was the world's first parliament, which then sat here for the next 8 centuries. But there's another reason why this is an important place. Although they didn't know it, those early pioneers of democracy had set up the parliament in the shadow of a most extraordinary rock face.
From the air, you can begin to see just how unusual this rock face is. It's a crack in the Earth's surface that runs for hundreds of kilometers. But what we're looking at is just a tiny part of something much, much bigger.
This is the edge of a gigantic slab of the Earth's crust which runs unbroken for 7,000 kilometers, right from this point, under the Atlantic, across the USA, all the way to California.
It's what's known as the North American Plate. Just 20 kilometers beneath Iceland is a vast column of superheated rock, known as a plume. Recently, the shape of this hot plume of rock has been mapped. It's 100 kilometers wide and at least 600 kilometers deep. Created more than 50 million years ago, the plume is sustained by heat continually rising up from the Earth's hot core. It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in 2 directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move.